So let's talk about this a little bit more. How are we going to enable science and exploration as we go to the moon and to Mars? So to lead this session, we have Noah Petro, lab chief at NASA Goddard. When he was a student at Bates College, he was introduced to the field of planetary geology. And after receiving his PhD at Brown University, his passion has led him towards understanding the geology of planets, especially the moon. Studying the composition of the moon, other small bodies, and Mars via remote sensing allows him and others to identify interesting areas to explore. Noah, take it away.
Wow. All right. Following Lori is always a challenge. This is not the first time in my career I've followed Lori. I will try to do as best I can, but Lori sets the stage very well for all of us. It is a real joy and privilege to be here today with all of you. Right now, in our exploration of the moon, feels to be one of the most exciting times in lunar exploration in several decades. The last couple of weeks has seen some of the hard work that people on this stage, people in this room have put in to get us in a position where the things that Lori talked about feel a little bit more real. And so we're going to talk about not only the engineering, the technology that's needed to sustain lunar exploration, but also the science that we want to do and get out all of this. I'd like to start with a short introduction. Each of our panelists take a moment to introduce yourselves to this august group, and then we'll get into some discussion. And I will try to preserve some time for audience and Zoom Q&A. So why don't we start with my friend and colleague, Brett Denevi.
Hi, I'm Brett Denevi. I'm at the Johns Hopkins Applied Physics Laboratory, and I'm here to kind of represent the lunar science perspective on the panel. I've been working on various aspects of lunar science that I think are really, benefiting from all of the architecture work happening now. That includes lunar reconnaissance, orbiter. I specifically worked on the cameras for many years with Noah here. I'm working on several of the scientific payloads that will be delivered by our commercial partners, some of the CLIPS deliveries. That includes lunar vertex, which will be going to a magnetic anomaly on the moon. There's a mini magnetosphere there, so trying to understand, how this magnetic anomaly formed and how it protects the surface in those areas from radiation. That'll be delivered by the Intuitive Machines 3 lander. And then an upcoming one after that is called Lunar Vice. It's led at University of Central Florida by Carrie Donaldson Hanna. That is going to be an incredibly ambitious delivery where a Firefly lander will land atop a volcano, a silicic volcano on the moon, to try to understand how we get these very unusual compositions that we don't understand how they form on the moon.
Not that far away.
How's that? All right, good. And then finally, the most ambitious and kind of time-consuming one right now is I'm leading the geology team for the Artemis 3 mission. So there we're working to set up really ambitious and important science goals and objectives where we can answer some of the most important questions that have been identified for planetary science that we can do at the moon, and then plan out how we can accomplish those goals. That includes, setting up the EVA plans, the sampling plans, and my daughter likes to sum up my job to her friend by telling them that my mom will be telling the astronauts which rocks to pick up on the moon. I'll leave it there.
All right. Hi, everyone. Can you guys hear me in the back? Sweet. Hi, my name is Michael Nyack, call sign Orbit. I'm a planetary scientist, pilot, and program manager at DARPA by background. So my take on the moon specifically has to do with commercial. So as regards all of the human spaceflight exploration, I'm one of you who does not work at NASA. I have my NASA sticker and I'm cheering. But my specific, from a DARPA perspective, my job is not to complement human spaceflight exploration, but rather to complement commercial exploration of the moon. So think about things like infrastructure, how to have commercial services on the moon, and leverage all of the work that NASA is doing to benefit commercial industry. One specific example I can give of the difference, right, complementary but different role that DARPA is playing to support NASA is, for example, where Brett is studying mini magnetospheres. I'm I'm a planetary scientist by background, so I've also studied mini magnetospheres in the past. And so work I'm funding, for example, is to study whether there is excess power being generated from the potential energy that is being stored within mini magnetospheres, whether there's excess power available and whether that can be monetized, right? So it's not the science of lunar anomalies, it's what could we do with it to create, a commercial service like power, logistics, comms, PNT, take your pick. And so along that line, I've run programs at DARPA called Luna 10, the 10-year lunar infrastructure architecture. We've got another ongoing investment called Logic that creates a commercial consortium for international, private, and academia to join us along this journey.
Thanks.
Wonderful. Yeah, I'll do my first introduction. I think we have some charts. Yeah, my name is, try not to be too loud. My name is Jody Paredes Garcia. I'm the corporate chief engineer for Firefly Aerospace. I've been the chief engineer for the Alpha launch vehicle, a 1-ton rocket, for the last 5 years, since inception to now that it's getting to rate. Before that, I spent 7 years learning and working at Jet Propulsion Lab, doing mostly rovers and landers, doing Curiosity, Insight, Perseverance, and also some spacecrafts like Europa Clipper, currently going towards Jupiter. And yeah, that's been mostly my background. Are we gonna go through slides?
I would look, yeah.
Yeah, you have that.
Clicker up there, push the down
Oh.
button.
Cool.
Once they get.
Oh, okay.
Yeah, because then
Never
again,
trust a scientist with a clicker.
yeah, then I'll just explain quickly what we do at Firefly. And I wanted to show a brief 1-minute video because as we can say, yeah, we have rockets, but we are a space transportation company. We try to offer rides to space to allow science and all these amazing things we're looking for to get there. And once we are in space, then it's up to you guys to act. I gotta say, like we successfully completed our Blue Ghost mission 1 that just on Sunday. Yeah, thank you. Yeah, just on Sunday, we finished our 14-day mission with full 60 days since launch to landing. And we can say we're the first probably company from the United States to land successfully on the moon and perform all 100% mission success. All 10 payloads from multiple centers, NASA, were able to succeed, complete their mission. We got over 119 gigabytes of data. 56 of those are just science-based. So again, mission finished Sunday. So we still have a lot of things we're learning. But yeah, it's been very, very amazing. So here, if we can click the video, we'll just show, this is what we do at Firefly. That's not only landers, but we do 1-ton rockets, 16-ton rockets. And I'll let the video talk. Yeah. That's our mirror on the engine. All right, I'll go quick because I know we have a long, interesting panel today, but mostly we're just a small company, 750 people, but we have a lot of products that we share. We have 4 of them, rockets, landers, and spacecrafts, and we share a lot of technology across each other, a lot of lessons learned. And I think that's partly why we were able to like succeed on this last mission, because many of those articles, components, hardware had already been flown on Alpha that we can test and had been qualified. And obviously we work with our partners at NASA that helped us, find the right standards. And then, yeah, first commercial lunar lander to successfully land. And we have the only currently 1-ton rocket flying. And we're developing our larger rocket to provide an alternative service to a Falcon 9, which we all want to have more rides to space. And we're trying to do our best working with Northrop Grumman on that. So launch, land, and orbit. And then, interestingly, we also have carbon composites as our primary core technology that we used on all rockets and structures, as you can see in here. A lot of technology that shares. We try to go as simple as possible. That's why if you see our engines, we don't have gas generators. It's a patented top-up cycle. We try to learn small with Alpha, then take it larger to MLB, And then we try to do also the landers, go small, things that we have already done, COPVs, struts, GNC, navigation, all that, and then slowly try to put it in and increment the technology maturity of our company to succeed for our customers. And I'd say this is kind of our vision for 2030, and it will come up later today, but I think that's where it's important that we have a good understanding between government and private sector. How do we partner for this? Because as Lori was saying, you know, 1 year is 1 day in this industry, and we cannot just plan, you know, quickly on these things. So this is our vision. With Alpha, we can supply LEO, SSO, MEO. We can also partner and have our own spacecraft, Elytra, that's going to be flying out. Blue Ghost Mission 2 is going to have an Elytra article on it, which is going to be orbiting the moon as well as landing. We have our Blue Ghost, as everybody knows now, we landed on the moon. We have Blue Ghost Mission 2, we have Blue Ghost Mission 3. And then again, it's that partnership. Blue Ghost Mission 2 is going to have an orbiter as well. There's a lot of science that we can do, commercial and private. And I'll just show here, like the last video. Let me see if it works like that, because I think it's very worth it.
Blue
This is
Ghost
the-
Riders, path to the stars is no longer limited to nations alone. Firefly is building the road to the next frontier, one mission, one dream at a time. Tonight, we didn't just reach another mission milestone. Together, we created a moment in history.
Paul Khan, Chief Engineer on Ops. Y'all select the landing. We're out the door.
Thank you.
Now I gotta go to that. Oh, man. I will say one of the things that was not shown in that video, but was the picture of the Earth during the eclipse. I kept thinking to myself as I saw it, how if you squinted really hard, you'd see me in Alexandria, Virginia, screaming at the clouds at 2:30 in the morning. But there we are. And what was so important about that image is that there were people all across our hemisphere looking up at the moon in that moment. And some of them might have known that at that moment in time, there was 2 spacecraft on the lunar surface that had just landed. There was 1 in lunar orbit that was surviving the eclipse to image those sites a few days later. And I think was the crowning moment of that unprecedented 2 weeks in lunar exploration, certainly in my lifetime. As we sit here in mid-March of 2025, looking for a very exciting several more years of excitement at the moon, I would ask this panel right now, having accomplished the Blue Ghost Mission 1, having seen years of development and decades of scientific progress in understanding the moon, what are the biggest technical and logistical challenges for the next phase of returning to the moon? And I'd like to start with Mikey to answer that question.
Yeah, sure. So I think this is one of the things that we looked at with Luna 10, taking a fresh look from horizon to horizon at what the limiting challenges are. For those of you who are familiar with DARPA's role in the tech ecosphere, it's to try and attack those problems that, you know, today seem impossible. Perhaps we can provide some hint of how it could be solved in the future. So I actually think there's a as far as I see it, there's a fork between technical challenges and logistical challenges. Technical challenges to me is very simple. It's power, which everything we want to do on the moon, especially as it comes to commercial, centers around power. So a lot of things like commercial mining, for example, that's a megawatt hour enterprise. If you want to do things like comms, PNT, persistent survive the night, it's a kilowatt hour enterprise. And at the moment, we're at the watt hour enterprise, right? Everything comes with you. So happy to see such a massive success. But there's nothing that rover could power that is not today directly attached to the rover, right? So we need to get off board. And so I think the largest technical challenge is scaling to megawatt hour power on the moon, such that, you know, future missions being designed by Firefly and other commercial companies can show up, plug in, and you don't have to bring a megawatt hour enterprise with you. Now, along that note, scaling, I think, is the major logistical challenge to date, right? Everything we have done has set us up for single important efforts. But in order to create an interconnected web that actually scales, I think that's a huge logistical challenge. The analogy I like to use is, I can show up in this room today. I can find a place to plug this in and get power. And that's because, I might have to look around a little bit, but the infrastructure already exists by which I can power this device. And so getting to that place logistically is a huge challenge. And so transportation across the moon. Now, we're not there yet, but in terms of a DARPA vision of seeing kind of 10 years into the future, once we start having persistent commercial landings, and it's so exciting to be able to say we have one fully successful mission, and there will be more from a commercial enterprise. As more and more start to arrive, we don't want the science and the exploration to be limited to the vicinity of where that's happening, right? We want to be able to scale outward. And so transportation that is more ambitious than, rolling along a difficult terrain, because the lunar surface is a vengeful place. We want to be able to get there. So there's much more work to come. I see those as the big challenges: power, scaling to megawatt hours, and then scaling logistics for transportation.
I would say the moon might be harsh, but boy, we know it well.
Yeah.
And it's forgiving if you're allowing yourself to explore. And thanks to the work of Brett and all of the other scientists on LRO, we've uncovered the moon to reveal how it is at a scale, as was mentioned before, that is unprecedented in planetary science. So Jordy, from your perspective, with Lugos Mission 1 under your belt, what's next? And what do you see as the next big challenges for the next era of lunar exploration?
Yeah, so I'll say we're still going over data over the last couple of days, but I'll say maybe the biggest challenge that we were not prepared for, or we were not expecting, was like the thermal environment. We have a lot of analysis and a lot of predictions, and I would even say we know maybe better Mars than the moon on that topic, because we have more data. We had our analysis, and we had 500 hours of just simulations of landings. We got landed on the moon, and things were getting warmer than we expected, and we was like, what's going on? We have our very precise thermal models that we have been developing over years, working with our NASA partners. And it turns out we actually were getting reflection from the nearby crater that was actually warming up our lander more than we had ever predicted. And we knew how that area was supposed to look. We knew that crater was supposed to be there, but we had not predicted that reflection could actually increase our temperatures. We got up to 250 Fahrenheit. And during the eclipse, we're getting down to minus 275 Fahrenheit. Right. So I think that's one, the thermal management is a challenge. We were able now to actually anchor our models and predict that reflection and have it anchored. We had to make some challenges and turn off something here, try to work with the radiator, but thermal management, it's something that for landers, and then for human exploration is going to be a challenge. And as you said, we need power for that. Right now we go by solar power. We last 14 days, right? When we got, nobody has ever been able to survive the 14 days of darkness. And I don't even know if with radioisotope generation, radioisotope thermal generators, we could get to a point that we can at least maintain the hardware steady. But as you said, we need power for that, and that's something that we are very excited and would like to work with the government, and how can we make sure that we can survive that time. Power is one, and the other is dust, right? That's and regolith. We studied that during landing. As you can see on the video, we had Lugri that was studying the impact of regolith. And we could detect that, the efficiency of your solar panels, the efficiency of your thermal radiators was affected by dust. That's why on Lugos Mission 1, we also had one instrument that was actually testing new technology to try to get rid of that dust, because it really affects your efficiencies. And if you want to be there, not just 14 days, but you want to be there for the long run, we have to work that. So these are kind of new technologies that we want to find a way to resolve.
Excellent. And now, Brett, from your perspective as a scientist, the benefit of all of this technological advancement is science. So what do you see coming into Artemis 3 and out of Artemis 3 as places where what we can do on Artemis 3 will feed 4 or 5 future Artemis missions, future robotic missions as well?
Yeah, that's interesting, because as I'm listening to this, power, thermal management, mobility, those are all things that have huge effects on the science that we can do. The one where I start to disagree is dust, because while some people see dust as this annoying hazard, it is in fact a scientific treasure that will teach us about the evolution of the moon's surface. So, but yeah, especially, when we're talking about the smaller missions, the science, we want to be able to operate throughout the day. So that involves planning for operations that it can extend through these really hot periods on noon, rather than having to hibernate. And then eventually, throughout the very cold and long lunar night, there are so many scientific investigations that cannot be completed in just a single lunar day, but require a very long baseline of measurements. In some cases, especially when we're talking about like geophysical things where we want to measure the seismic activity of the moon to understand its interior structure, those can require years of operations. So that's where we want to work toward on those. And then, Artemis 3, especially as we're looking at mobility, that will be a huge driver of the science that we can do. Artemis 3 will be 2 crew members exploring the exploration zone around the lander on foot. They will not have a lunar terrain vehicle yet, as we heard from Lori. So the kinds of mobility constraints that go in there then are walk back constraints. How far can they walk back safely in the event of an emergency, or communications? How far can the communications infrastructure extend out, and does that depend on line of sight to the crew members? So there are all kinds of parts of the Artemis 3 infrastructure that will really affect the kind of science and the mobility that crew members can do. And so as we're working towards eventually having the lunar terrain vehicle and extending the reach there, that will be incredibly important. And then just the suits and all of the capabilities of the suits too, that will control what kind of environments the crew members can operate in on the surface. So a lot to keep track of to make sure that those decisions are continuing to enable science.
Excellent. Well, I'm sure everybody has dozens of questions to ask this panel. Now's your chance. So I'll pause for a moment and allow this august group. I see hands, which is great. It's not just hands in teams anymore. It's hands in person. It's fantastic. So we have on the left side.
Jordy, I find it interesting, the comment you made about the fact that we know more about Mars than we do about the moon, and which actually begs the question of why not have more robotic lunar missions, maybe in parallel with Artemis, maybe preceding Artemis. Any thoughts about that?
I can bring my thoughts. I think let's go. I think from our side, we're ready. We have a lander that works, and I think we just need to obviously, work with NASA and all the other departments that are interested. I fully agree. Again, my experience was at JPL doing rovers on Mars. I think that was great, and we learned a lot from all of these small little guys landing. It was 469 kilos of dry mass. I think there's a lot of technology demonstrations that can be lowered down, and risks that can be brought down by landers. So I think Firefly, we're here to supply the needs of humanity on this point. So we are ready to make more landers, and we're ready to support where we think the science needs to take us.
And I would say the CLIPS program, I think, has got a very ambitious schedule for landers. This was the appetizer the last 2 weeks. The main course is yet to come of multiple missions to different locations, not just the South Pole, but to that exotic volcano that Brett was talking about, to the swirls, the magnetic anomalies. And so I think we will see the parade of landers to the surface to help fill that gap in surface experience. And maybe we'll catch up to Mars once again from the moon. But I would just say stay tuned for some more excitement. You guys have done a good job raising the bar. Other questions from the Zoomiverse or in the room? A hand on the left-hand side here.
Hi, I'm Stephanie Scholar-Dews, NASA Goddard. This is really exciting. Thank you all. I have a question that may be more for Lori Glaze, and that is, those of us who work for NASA got a lot of emails over the past couple of years about the Artemis Accords, and I'm just wondering about the significance of those and the, the aftermath.
Thanks. It's a really good question. If I remember correctly, we're now north of 50 countries that have signed the Artemis Accords. The real, I think, significance of those signatories and the relationships that are being built there is the commitment on the behalf of those countries and their governments to adhere to certain principles about how we peacefully explore space. And that is the real significance there, is a kind of a consortium of nations from around the world that are committed to that peaceful exploration. That is the key piece there. And I'll just kind of as a point of distinction, because sometimes folks get a little bit crosswise on this, we have additional partnerships with some nations, a few nations, which are government to government formal agreements to supply hardware or something like that. So the Artemis Accords doesn't necessarily automatically buy a partnership, right? It doesn't necessarily become part of a partnership, but it does open the door for conversations. We are certainly looking for opportunities to work with, in particular, emerging nations that are now part of the Artemis community. Thanks for the question.
One more question in the audience there.
Got one. Yeah, thanks, Noah. So thank you all for everything that you do. This question is starts with Orbit. With all of the interest of coordinating across the different commercial companies and the complementary nature of their capabilities, right? There's a real need for enterprise integration and ecosystem engineering. I believe your program has invested in digital engineering to help that community in that way. Can you speak a little bit to the value of that approach to providing a common engineering environment for the players in the game?
Absolutely. Especially and it's a timely question, because in the past, for example, when it was just government efforts, right? I will give you a requirements document. You will maintain to that requirements document. Today, in a commercial ecosystem where I'm asking you to provide me with a service, really, you could provide that to me in any way possible. And it benefits all of us to redo work as little as possible. So digital engineering is one tool, but I think your question was larger about just general engineering tools that we can all use. I think there's two answers that I would give to that. The first is IP boundaries. So as we go on, and there's more and more commercial players that are competing for a limited ecosystem, the companies that are able to bring down IP barriers and share resources, whether that's engineering resources, certainly, but I would argue even more, right? Science resources as well. Those are the companies that are going to be exponentially successful. And this is one of the models that we tested in that program, which is that a lot of companies came in with 6 pages of IP restrictions, and we struck them down. We said, you can't play, you can't join if that's how you want to come into the ecosystem. So tools are one place to start. Software is the next level. People is the final level. Getting companies, and I think we're in a place where you will see more success that way, and one success begets another. The second, and this is one that we're actively exploring with consortiums like Logic, is standards, which is that not every company is ready yet to make a large commercial investment, but they're certainly cycling up to it, right? Through single missions, through NASA partnerships, through other partnerships. The question is, when private enterprise comes in, they're going to want to see certain value propositions, certain return on investments. I think the way we get to that is with common standards, one that is not just across the government. It's not one person dictating you will maintain this, IEEE standard for power, but one that is interoperable, and therefore it just makes sense, and therefore it goes forward. So one of the things that we're pushing to do with Logic, which is the Lunar Operating Guidelines Infrastructure Consortium, run by the Johns Hopkins Applied Physics Lab. And so in our first year, it was a consortium building effort, and we were looking for standards, places to overlap. But now we're seeking to go toward, making what I just said practical. What are the experiments that one company can do with another in order to break down barriers? So returning to your question about digital engineering, one of the first experiments we're going to do centers around digital engineering, because while we can't have 50 companies yet going to the moon, we certainly want to live in that world. There are ways to simulate how 50 companies can share resources with each other. So that's absolutely where we're headed. A really timely question.
I think there was one other question in the floor.
Hello, thank you all very much. It's been very interesting listening to you. I'm Rita Wilcoxon from Leidos. I was wondering about on Blue Ghost, all of the science that was on there. I think you said 56 different experiments.
No, 10 different experiments, about 56 gigabytes of
Oh,
science
gigabytes.
data. Yeah.
Okay. All right. Well, where can we learn about those? What they learned while they were up there, what they did while they were up there? Is there someplace we can read about it?
Yeah, so all the data was distributed to the customers at NASA, Johns Hopkins. I'll have to find out exactly how the public, but usually what we track as a private company, we offer the right, and we're going to track how many research papers, PhDs, master thesis come out of these, and usually it's going to be to the customers that created that hardware and those payloads to publish that data and those results.
Yeah.
But it'll take some time.
A little bit, yeah.
One of the important things that comes from this is for all of the NASA-funded payloads, all of that data will be made publicly available in the planetary data system. And so that is a really important part of this, making sure that that data is shared and can be, interpreted and used for new purposes as well.
Yeah, so
And I'll
what-
say years later, we find utility. I got my PhD off of a 1999 NASA mission and then a
It was just yesterday,
2010
though, wasn't it?
Japanese mission. Yeah, just because that data lives in PDS. So,
So
new
the-
grad student come in and
The,
try
the
to.
NASA Planetary Data System is one of the, I don't know, it's one of the unsung heroes of NASA, and we have a lot of unsung heroes making all data that NASA Planetary Science Division funds publicly available after a period of time where the science team can actually dig into it. And they're just starting that. My second question is going to be about this little waiting time that we have, but the team will go through the data, calibrate it, and make it usable. And so typically it's 6 months, I'm not quite sure, but there will be a period of time and when all that data will be made available for all of the students, and not students, to dig into. And my great joy is to see what the surface measurements say compared to what we learn from orbit from a mission like LRO. So for instance, the thermal differences, hey, let's learn about why that is and understand this robust and incredible data set that has just been collected.
Good.
Thank you.
One last thing. I'm actually kind of curious to see what there's a panel later on that's going to discuss, I think, private missions, public data. I'm kind of curious to see what answer they have for your
That's kind
question.
of why I brought it up because, one of the things we need to do is share more about what we're learning with everybody so that you can get more commercial interest potentially. And then I have one for Luna, your Luna efforts. Is there a follow-on activity to Luna 10 that you are planning?
Yeah, that's kind of timely. I regret I cannot give you a definitive answer, but I can say that yes, in the next month, we will be releasing something. So there's a lot of partnership that goes on in the background with NASA. This coming program will be with NASA and the U.S. Geological Survey. So keep an eye out. We're almost about to make that public. It is not public just yet, but there will be a follow-on. Thanks.
Yeah, sorry, I wanted to add in here that, as you said, there's like a difference between like the scientific data that we have and the spacecraft data that we measured. One of the reasons why we were so slow to get to the moon, took us 45 days, was for that, because we wanted to use that time to evaluate data. We did multiple slow burns. We could have gone much faster to the moon, but we decided to take it easy, do a small burn, increase elliptical orbit on Earth, measure, calibrate our engines, evaluate alignment. We had all of those data reviews live. It was do we go again in 2 days? Do we evaluate? Yes. Trim the software, play with this integrator. So like all that data was actually being evaluated, improved. And I think that's what slowly led us to have a fully calibrated system and land successfully on the moon. Some of that data is also going to be shared. And I'll say, like, for us, one of the items that we did to succeed to the moon was to go back in history and look at all of the landings that we have had on Mars, on the moon, see what anomalies had failed on others. And we have a very long table of any anomaly. It's like, is your lander susceptible to it? And then we did studies and we looked at, okay, that's not applicable to this. Oh, we could be applicable to this. So we actually worked it. And I think that kind of like shared knowledge would be very, very useful for the public, because we want to have other landers also succeeding, and we're going to have Artemis program succeeding, and all of those anomalies that maybe show up on us, I'm sure they show up on others, and then we can all prevent to it and have a more reliable landing system and access to the moon.
Absolutely. And along the veins of data and the pace of science. And I know I can't wait to find out the results of all of the experiments that NASA flew on Blue Ghost Mission 1, but it's going to take time. Time is the enemy of science because, at times, because we want fast results. We want to feed the machine that is the public interest. And so we want to get those results out as quickly as possible. For instance, on Blue Ghost Mission 1, on Artemis 3, we'll have retroreflectors, mirrors that are deployed on the surface. Now, mirrors may not seem like an important thing. We're in a room with mirrors along the walls, but mirrors on the moon give us a chance to get geophysical understanding of the moon, but it can take years to build up statistically significant data results from that experiment. So the cousin of the retroreflector that Brett and I will deploy, well, not personally, but we'll have deployed on Artemis 3, is working on the moon right now. And within, I think, the first 24 hours of being on the lunar surface, there were photons bouncing off of your mirror.
Yes.
Which to me is a breakneck pace of science. It's very exciting. Thinking about science, Brett, and thinking about Artemis 3, I think one of the great frustrations that we share is that the first year after the mission lands is going to be spent kind of assessing what we learned. What did we get in terms of samples? And that great bonanza of understanding what the samples tell us is going to take some time. Can you give us a preview of the types of science investigations, types of science questions that we are going to be asking our astronaut counterparts on the lunar surface in the Artemis 3 mission?
Oh, yeah, absolutely. I mean, some of the questions that we're most interested in are, really broad planetary science questions that have been high priorities for decades. So we're really thrilled to be able to kind of target important areas and select samples that'll help answer those questions. Those are things like, what was the bombardment history of the Earth-Moon system throughout time? So that's interesting. We're learning more and more about the current impact rate, but how does that extend back even into kind of the earliest period of solar system history, where things were a lot more dynamic? There were many more large objects impacting the Earth-Moon system. And so we're looking for rocks that have been melted by those impact events, collecting those and dating them to understand how they shaped the evolution of our system. We're looking at trying to understand other fundamental questions like, what is the moon's crust and interior made of? How does that tell us the story of how a planet forms and then evolves over time? And then some of the questions that, are really important and interesting scientifically also are things that we'll prioritize for analysis immediately after the mission, because they also have things that will feed forward very importantly to Artemis 4, Artemis 5 plus, and all future missions. Those really are things like what we saw during the Blue Ghost descent there, the dust plume rising, and then you even saw that one rock flying out over the horizon. So that is a really important scientific information there, but it's also important. We want to deploy instruments that will last on the surface for a long time. How are those going to be affected by that plume during landing and ascent? Others are things that are really important for planning scientific investigations in the future, but also planning for this longer sustainable presence on the moon. And that is understanding whether there is water ice and what its abundance and form and distribution is at the moon's south pole. So collecting samples that can give us the first piece of that answer. And maybe in the first year, we will not be picking those apart and understanding the full, isotopic distribution of all of the volatile elements in there to do the science that we want to do, because that part takes time to understand. Were these materials delivered by comets or asteroids or outgassing from volcanoes early in the moon's history? But we'll want to make sure that we're understanding just the general composition and abundance there so that we can plan for how to sample, how to use those as resources as future missions progress.
And I would be remiss if I didn't acknowledge the fact that, Artemis 3 is not, I guess it technically is happening in a vacuum, but it's not happening in the vacuum of other scientific. Dad jokes are, you get what you pay for. We have Da Vinci about to go to Venus. And some of what we learn about the moon's history will feed into the analysis that goes on in other missions as well. And that's an important part of why we're studying the moon, is not just to learn more about the moon, but to learn about the Earth and Venus. And yes, as a proud lunar scientist, even Mars, to understand our place in the solar system. And so we have to make sure we never forget that the work that Brett, her team, and the Artemis 3 science team does feeds into everything else that we learn about our solar systems that we're discovering around other stars. It really becomes the cornerstone, the keystone, the Blarney Stone of our understanding of how planets work. Thinking about future missions to the moon or future opportunities, how does the science results that you'll get from Blue Ghost Mission 1, from Artemis 3, feed into future opportunities for landed missions?
Yeah, so as we were talking, we currently have 2 missions coming up, Blue Ghost Mission 2 for 2026 and Blue Ghost Mission 3 for about 2028. Same lander, roughly the same lander, different instruments. It's just we made for Blue Ghost Mission 2, we're going to go to the dark side of the moon, which is
The far side of the moon. To be
Sorry,
fair,
sorry.
there's no dark side.
that's how
Pink Floyd.
we've been
gets
making the
25
joke too
cents,
much.
but, yeah.
Sorry, I apologize. Yeah. But yeah, we go there because there's a lot of scientific interest because of like the radio silence that we have on that area. We're also going to have, as we said, we launch, land, and orbit in our orbiter that's called Elytra. We have 3 versions of it. That's going to be our transfer stage. That Blue Ghost Mission 2 is going to have 2 stages. And we have a lot of commercial and also government instruments that are planning on being there and orbiting around the moon to help us on those comms and do studies on how that works. And then also provide telecom for our Blue Ghost Mission 2. Yeah, and I wanted to add to her point that we had 2 instruments on this Blue Ghost Mission 1 that had studied, it was like lunar planet vac. We put a vacuum system on and that studied like the composition and tried to do a quick analysis and look at the data. And that was Honeybee Robotics from Blue Origin that made that. And we also tried to study the inside and the temperature profile. Right, and that was also Honeybee Robotics with Blue Origin with Lister instrument. So we're all very excited to get that data and see how that plays out.
And again, a great feed into Artemis 3. I may be very, Artemis 3 heavy, but that's kind of my job, I guess, at this point, is the retroreflector, the mirror. Again, now Artemis 3 will add to that, building up this geophysical monitoring station of understanding the libration of the moon. Decadal relevance, high priority science for NASA. We're deploying a seismometer. Seismometer may not last 10 years as we got to with Apollo, but we may hope to last up to 2 years. And if other commercial missions land and other missions land with seismometers, the beginning nascent stages of a geophysical network. Lori talked about how Artemis 3 is effectively a test mission, but it's a test mission with tremendous potential for advancing scientific understanding of our nearest neighbor in space. And when you couple what Artemis 3 will do with what commercial missions, NASA missions to the lunar surface will do, we are in this new era of lunar science, of lunar exploration that is so thrilling. It's what I may be on the younger side of the crowd here, but I've been waiting my whole life for this. And so, as you said, let's go. Mikey, any thoughts on how science and scientists in particular can better, let's say scientists in the commercial sector haven't always talked on the same page. How can we do better to help you achieve success?
That's a great question. I think that speeding up is a big part of it. And what I mean by that is that commercial companies live on a fundraising cycle, right? So they need to show results. They need to go to their investors and say, here's what I delivered for the lunar science community. They want more. Unfortunately, having been on the academic side as well, sometimes it takes 2.5 years to peer review a Nature paper, right? So even, preliminary results to the archive are helpful. This is something that's been huge in the astrophysics community. I'd like to see the planetary science community push more of their, if you're going to publish a paper that's behind a paywall, put it on archive first, because then at least we can all look at it. Things like that, right? Because that helps the companies move faster. It helps them make their value proposition clearer and helps them open up new communities. The second is I would love to see education with industry is this interesting program that the DoD has had for a long time, which is spend a year outside the government circle. And it's not a bad idea to be able to embed for a little time as a scientist to go work with folks that are building lunar hardware, especially now as there are more and more growing opportunities to be embedded with a team that's moving quickly, perhaps making some rough assumptions. I think that can be a two-way value stream. I'll provide you some valuable input to how this is actually going to be used as you're trying to move fast and break things. And in return, I can build a partnership that I can then take back to the agency where I work. And as we, again, get more and more and more landers, people, crews involved, we can learn such that we don't take unnecessary risks.
Yeah, I think the one challenge in speeding up is that, again, you can't speed up geochemical analyses. You cannot speed up sorting through thousands of centimeter sized fragments. But what you can speed up is the reporting of, hey, we got this. Sometimes the nature paper is the great result. As we'll talk about in a little bit, is the fruit that is born from the seeds. It's just as important to talk about the seeds that you collect, the data that you have harvested as the results are. And, you know, we can show the future promise of those results and highlight all that great work that comes. But I think you may need to help us understand how to get that appropriate amount of speed behind us would be.
And
So
that's my hope, right? Something like an education with industry, maybe we can arrive at a happy medium.
I think we've all gotten used to finding happy mediums in the last several years, and so let's work towards that. Another happy medium is another opportunity for questions from the room, from Zoom. We have 2 questions in the internet space and at least 2 questions in the room here. So why don't we go to whomever gets the microphone working first? There we go.
I think I've got it. I'm gonna just step up here so they get somebody on camera. Are there any plans to replace the unique high-resolution imaging capability provided by LRO?
Well, it's a fantastic question. At present, firm plans, no, but there has been an ongoing study led by a group of us at Goddard and some external partners from across NASA to look at what that would look like. What would it mean to have an LRO successor mission? My ideal is to have LRO operate as long as possible. In the next week or so, we will find out if LRO, knock wood, gets another 3-year mission extension to take us to 2028. Not bad for a 2-year mission. That would be, let's see, 18 years. So driver's license and just about ready to go off to college. At present, it's just in that pre-phase A study period, but we do have our eyes set on a robust mission that would meet the needs of the exploration community as well as meet kind of the needs of the orbital lunar science community. Recognize, hey, LRO has given us so much, continues to give us so much, but we want more. We want not just higher resolution, but different types of data to understand volatiles, to understand the environment that we are creating when we go to the moon through landed missions. So everybody, I hope, keep your fingers crossed for the Lunar Exploration Science Orbiter, LEXO. Just all of us at Goddard are pushing hard to make this dream a reality. Another question from the room.
Thank you very much for this. It's incredibly exciting. My name is Oreste Realem. My question relates to the idea of Artemis as a sustainable base. And of course, related to that goes the potential of exploiting the lunar resources. This is the question that I keep asking, and I get negative responses. So what is the future thoughts about the idea of mining titanium, for example, from the ilmenite, which is, of course, very abundant on the regolite, or also the idea of extracting things like helium-3 that could be used as a potential fuel, or also the idea of exploring the potential of extracting water, not just from the ice at the South Pole, but the mineralization water that is trapped in the regolite keeps evaporating, sublimating actually, and then refreezing during the lunar night. So is there any plan from a technological perspective, very far-fetched, that is trying to consider those resources to make the base more sustainable?
Thanks, great question. Oh, go ahead.
I mean, there is a ton of work going into this, of course, of all of the ways that you could use the resources from the moon. And I think what we really need to do then is start making a plan to make sure those prove out and then start incorporating them into the plan for kind of sustainable Artemis. Artemis 3 will get some of the first measurements there and some data to help with that. Other robotic landers will as well, but kind of implementing that into a path forward is the next step.
Yeah, I mean, from our side, this is more on the set of the payloads looking for that. We're mostly offering like the rights But that's why, for example, for Glucose Mission 3, we're offering that rover that's supposed to actually go and look for those areas and try to do science and see it's like, are there waters in those locations that we can actually collect or not? And then combine it with what we've learned right now of like regolith collection. But I'd say, yeah, I'm very excited to see how rovers can do that. We did that on Perseverance with in situ resource utilization with like MOXIE. We were able to collect carbon dioxide and make it into oxygen that can then be used for fuel. That's one we use for our rockets. So I think we see that long-term path, and from Firefly standpoint, we are ready to support once these technologies are proven, and then we can actually go and implement the execution.
And I'm happy to finish because I think you asked a great question, and I hope my answer will illustrate how sometimes a different perspective can help, right? So from a purely commercial perspective, you asked about space resources on the moon. The issue that we have found, so unfortunately, or fortunately, I guess, I get to talk to a lot of VC and private investor folks. And let me tell you, they are really excited about the moon. They love it. They won't put a dime into it. And here's why. Because space is hard, the moon is harder, and they could put their money in the S&P 500. Well, maybe not today, but a few months ago, they could have put their money into the S&P 500, make 7% a year. What they're looking for, and this is what folks have told me, they're looking for the Uber, right? I want to invest $100 and I want to get $1 million out of it, right? I want to be an early seed investor in something that's going to pay off. Resources seems like it could pay off, but why are they not making the bet? Why are they not jumping in? The feedback we've gotten is it's the data. Lunar Prospector has 30 kilometer by 30 kilometer pixels within which I can make inferences about things like ilmenite and titanium and so on. That is just not, we know that's not how geology works, right? It's not evenly smeared across a 30 by 30 kilometer square. I need to get down and find loads, and that I can commercially exploit, sell that to investors, and actually bring back and benefit the Earth economy. That's the way that mining becomes commercial, as opposed to mining for science, which is still important, right? But how do we get VCs and PEs folks off the fence? And so fundamentally, right, as we looked at commercial services, and I apologize because it's a really good question. I want to make sure I give you a structured answer. When we look at commercial services, things like power, what is it servicing? Who's the customer? PNT, who is the customer? Comms, who is the customer? And the power, it's mining, right? It's resource extraction. That's who, if I'm a power company, I will sell to. That's who I'll sell comms, data, PNT, thermal as a service, whatever. So I need to get that mining to be profitable. That is the anchor tenant. And we're just not going to get to an anchor tenant place on 30 by 30 kilometer pixels. So one of the things that DARPA would like to explore, and so what we hope our next program will explore, is low altitude prospecting. So to turn those 30 by 30 kilometer squares into perhaps something that's more like 500 meters by 500 meters. We hope we can do even better. But the goal there is to get commercial companies to say, here are where in this dot and this dot and this dot, not this table, is where I should go. And the hope is that will motivate, and specifically, what are those resources, right? To the level that, Lunar Prospector was 1999. So updating that, I think, is the fundamental biggest thing we can do from a commercial perspective to create mining and resource extraction as an anchor tenant from a commercial point of view.
Let me just comment for a moment there. And, so one of the other jobs I have, not just Artemis 3, but LRO project scientist. And one of the reasons LRO had the suite of instruments it flew with was to help characterize the mineralogical composition of the surface, particularly for titanium. And one of the instruments that Brett spent the early part of her LROC career on was our wide angle camera, which was specifically selected to map ilmenite at better than that 30 by 30 kilometer scale. So I would argue, I would actually posit that we have the beginning stages of some of that data that's needed. And not to go on for hours here, which I could do on LRO, but that we're I think further along in understanding where those resources are. Maybe not for water or for some volatiles, certainly for titanium. I think, Brett spent a good chunk of the early 2 or 3 years of LRO looking at titanium abundances across the surface. And so I think we're further along in that. It's finding the intersection of, well, here's where the high yield titanium could be versus where do we want to go scientifically, and finding the intersection of that, something that I think we all are looking forward to. So let's as a scientist, let's do better at getting those results with people who want to send the missions to the surface. And again, every time you dig into lunar regolith, not only an opportunity for ISRU, but also for science. And so finding that happy medium is going to be super, super critical. Let's go. All right, we are nearing the end of our time here. This is where everybody in the audience goes, "Aw." We have we have questions flying around. My goodness gracious. Yeah.
Hello, I am a student at the University of Illinois. I just wanted to ask, do you see or are you excited for any new instruments or models that could help us explore the moon better or even address the challenges of landing on the moon?
Absolutely.
Yeah, absolutely. I'll say there's multiple technologies that can be used for landing. We used visual navigation as one of our systems. I don't know. I'm not sure if you guys saw some videos, but the lander was loaded with the surface of the moon ahead of time. And then we were using camera recognition to map what we were seeing and make sure that the lander knew what it was. And there's some videos that we posted on YouTube, but like that visual navigation was like spot on. You could move the video from what we were actually seeing versus what we had loaded from historical data and images, and it was right on. And that helped us a lot get there. There's other technologies that have been used, LiDAR, lasers. We're interested in all of these. And as we say, we're looking for more reliable landing mechanisms, looking for potential redundancy on the systems. So we're very interested to see like what other technologies we can actually add onto our landers to maximize chances of success on landing, as well as then on surface operations.
Anything that can go subsurface, even if it's a millimeter below the surface. So things like neutron spectroscopy and so on, things that can look beneath the surface are a complete mystery.
Yes to that too, but also just going to add in, following on with like the Lexo discussion and after LRO, one of the most important things we can do is, 25 centimeter images in stereo and starting to add in some of the multispectral data so that we can get at the compositional information, at the exploration scale. We have monochrome images, so we can look and plan out, but we don't have that for kind of color and composition to help plan our surface activities.
Okay, this is for DARPA, Michael. You talked earlier about commercialization and what we need to do as far as science and how slowly we can get to results. And Noah, you talked about it takes a long time. So my question is DARPA looking at digital transformation, AI specifically to help speed up what humans can't do? Like protein folding was done by AI. We tried forever and a decade to do what humans did. So are you doing something with that? Because that is our challenge. I can see if we're going to have an intersectionality between commercial, NASA, science, and advancing things, we're going to need that.
Yes, that is a fantastic point and question. So I have a much longer answer, but I'll keep it short. And I'll say that, so we have 6 tech offices at DARPA, and I am not in this tech office. So I apologize. I'm speaking, from my limited knowledge of their work, but the DARPA Information Innovation Office is exclusively, like they are the AI cyber office. And if you trace them way back in the past, they gave you little things like the internet, whatever. But yes, the data accuracy. And so, for example, some of the programs that we've run are trying to parse papers faster to find inflection points in fields, which field seems to be going in a new direction. There's a lot of work in that. I will say that, as you well know, I'm sure it's very prone to artifacts, prone to edge cases. I think that needs to get democratized a little bit more. That is something we're looking into, but only from a basic research perspective. I think there's more work that needs to be done to make it specific to a field, especially one as as safety critical as space.
So in our final few moments here, I do want to just give our panelists one last question, very quick answers. You're all in different parts of this enterprise of science. What does success for your particular corner of lunar exploration, lunar science look like? We'll go down from my right, further down. So Jordy.
All right. So I'd say for us, for commercial commercial partners, I've been developing rockets for most of my life now and landers, and it's very hard, and it's very hard to change and modify, change payload, change dimensions, change targets, change engines. I'd say what success looks to me is like it started with clips, right? These like, like the scientific targets that we have, try to find it affordable and make the commercial segment, fight each other, find it affordable, make it work, right? I think that was a great success to be able to show like we landed on the moon for $100 million, right? When it used to be orders of magnitude for that to get something similar. We showed to the world that this is possible, and this partnership between commercial and private sector is very, very useful. I'd say success would be if we can work together on this like long-term vision and long-term goal. Because as we said, this hardware, this rocket, these landers cannot be changed every couple of years. I'd say if we find a way where we can standardize those products, like if we have a Blue Ghost lander that it services a certain amount of science projects that we have, if we can standardize that production to like 2, 3, 4, 5, and multiple of those, we can much lower the cost and increase the reliability of a system that we know we understand. If we would change every Falcon 9 every couple of flights, we would not be flying 100 a year right now. And I think that's what we could get if we are able to standardize like the payloads that we want on a Blue Ghost, and obviously a rover that we'll get into. And it's not just one, it's 20, 30. We, as private partners, we can actually force production improvements, reliability improvements, and lower the cost and increase reliability, but not on onesies and twosies, because there's all that non-recurring engineering that eats a big chunk, right? Now that we've done our Blue Ghost, making the second, the third, the fourth, it's much more affordable than for us. It's like the rockets, right? We started very expensive, 225 million. Every time after that, it's 15, right? So that's the goal. And I think we have this vision of like, how can we size our spacecrafts and landers to provide the needs for the next 5 years, the next 10 years, the next 20 years? We can make sure we get that developed and get that reliable and working for this industry.
Great. Thank you. What does success look like? I think big picture, I want to see a lunar Fortune 50. It's small picture, I would like to see one commercial service, right? I would like to see, so not necessarily deliver, but power as a service, robotics as a service, comms as a service, whatever, right? There is enough of an established industry on the moon that a peripheral player can come in and provide a service to them, just get the check from them, and return that to Earth. That would look like success. Brett.
Yeah, on the small side, and it's still actually very big, is we have all of these incredible science questions that we want answers for that will come in part from Artemis 3, but those also are going to take on, the follow-on missions. And then in the bigger picture, I think success really looks like being able to share that science and the joy of science and exploration with everyone, and having the world be reminded the moon is beautiful, it's scientifically exciting and interesting, and that we should keep exploring.
So in closing, I just want to thank the panelists here. Thank you very much. Great job. And I have just a simple request for everybody is, if you have time while you're here, go down about 2.5 miles down the road to the Goddard Visitor Center, which is a great visitor center. We love it. But out in front of the visitor center, there are 2 trees. There's a tree that was planted in the mid-1970s from a seed that was flown around the moon on Apollo 14. And we have a seedling of a tree that is seed came from the Artemis 1 mission. And in November, we planted that Artemis 1 tree. And we planted it in the winter to give it the best chance of survival. You plant a tree when it's about to go through stress and strain. It's going to go through cold, dry, windy conditions. So that tree has the best chance of spreading roots, of future success. And I think in lunar science, or in science in general, stressful times, strain can lead to deeper roots. But part of what makes those seeds turn into fruit, and those fruits are those science papers, those nature papers, data, rocks and samples, requires support from other trees, whether it's the Apollo tree shading the Artemis tree, or all of us in the room shading each other. We're going to need each other's support to see this success come through. And so all I ask in the next hour, week, month, years, decades, is for that shade and protection so that we can foster this next era of lunar science and exploration. With that, I thank you and turn the ball over to the floor.
Hi, I'm Takuma Hamanaka. I'm currently a sophomore at University of Illinois, Urbana-Champaign, majoring in aerospace engineering. I'm originally from Tokyo, Japan, and I look forward to a career in human spaceflight. I just want to take this opportunity to thank AAS for continuing to invite Liquid Rocketry of Illinois to these symposiums. We'll now take a break with snacks and beverages on the bridge. Enjoy the networking and building new connections. Please come back in 30 minutes for our next session on artificial intelligence and space exploration. Thank you.